Hello everyone, I am Ömer Farkbodur from Physics Department. Today I will present our Physics 212 project. Our project is the relation between the temperature and the forward voltage of a laser diode. As we know, the semiconductors are used in the electronic devices. Hence, the understanding the behavior of the semiconductors are important for the scientists and engineers. In this aspect, we aim to show that our experimental data aligns with the previous works and theoretical explanations. And we will move on to therapy. To understand these relations, we have to use some statistical mechanics, especially Fermi-Dirac distribution. As you see in the left part, we see how our Fermi-Dirac distribution changed with the temperature. At t equals 0, it behaves like the step function. We see no electron in the conduction band. We get the equation number 2. At t is greater than 0, we see some electrons are in the conduction band. Hence, we can use the equation number 1, and when we integrate it, we get the equation number 3. At low temperatures, the value inside of the logarithm is very small. Hence, we can approximate it as follows, and our equation becomes 4. Finally, the number of excited electrons over the ones in the valence band at t equal to 0 can be written as follows. This gives us the idea about how conductivity and the number of excited atoms change due to temperature, and we will move on to tight binding model. In the tight binding model, we have a few assumptions, which are the atoms have one orbitals, and we will only consider the hopping in the nearby energy sites. And we have a Kronecker delta function. When we constructed MN, we get the following result. By using the variation principle, the wave function can be written as the linear combination of the base of the orbitals, and these orbitals are orthonormal. Then also the time intervention equation can be written as the base of this orbit. And to use this equation, we have to write this equation as a component-wise matrix. And when we plug into values, we get the following. From the Bolos equations, we can represent our CM as a plane wave. And when we normalize it, we found that A is equals to 1 over square root of n. And when we plug in the value, we get the dispersion relation for energy. A equals to epsilon 0 minus 2j cosine ka. A is lattice constant in there. For the computation results of our experiment, we use the dispersion relation for tight bounding model, and we draw it in the first graph for the theoretical solution. In the second part, we represented our H as a matrix, the matrix representation of the Hamiltonian. And the diagonal matrix of the Hamiltonian is epsilon 0, and we constructed H and M. For the n represented the row number, and m represented the column number. When the difference between n and m equals to plus 1, we have a minus j. And when we solve this, we get this result. From the figure, it is evident that the numerical solution closely aligns with the theoretical solution of the dispersion relations, providing a reliable estimate. And we will move on to our equipment and circuitry. In the for phase 1, we use the Peltier to cool our diodes. For the phase 2, we use the dry ice. As you can see, we build our circuits like this. And we conducted the power phase 2 in the outside. And we our ladder that is worked, and the values we obtain are this. While the data obtained from phase 1 can be seen from that, and it is nearly linear. So we use the linear fit. And the value we obtained for coefficient is 0 minus 0.01 V voltage over Kelvin. But in the second phase of our experiment, we found that our voltage is 4.48. And we interpolate by using the transition point, and our graph is like this. As a conclusion, in this study, we used the band gap structure and the typizing model to investigate how temperature impacts the diode's forward voltage. We made sure not to touch the dry ice with the bare skin and refrained from using it indoors for safety reasons. The primary causes of the measurements inaccuracies were ambient conditions and our equipment's sensitivity. Deviations were also brought on by heating the diode over 10 Celsius and using the lot of circuit equipment. Our main discovery is the band gap, which in turn affects the forward voltage of the semiconductor laser diode. It's directly impacted by temperature. Thanks for listening.